Atrazine is a herbicide that is applied to crops in agricultural fields, primarily used on corn and sugarcane. It is particularly pervasive in Iowa, Illinois, and Indiana, where corn production is prominent. It is the second most widely used herbicide in the US, but it has already been banned in Europe. Atrazine is used as a pre- and post-emergence control of weeds. It works by inhibiting photosynthesis in plants and interfering with other enzymatic processes. Triazine herbicides such as atrazine bind with proteins in the chloroplast of photosynthetic organisms, therefore inhibiting the formation and release of oxygen. Atrazine may enter the environment in any ways. It can be dispersed in the air during application, and it can attach to dust particles that can be blown long distances from the application area, only breaking down by rainfall. It can also enter water bodies like streams, lakes, and rivers via stormwater runoff, or infiltrate the soil where it can remain from several days to a few months, typically over a period of one growing season. From the soil, it is absorbed by the plants through the roots or foliage, but it does not bioaccumulate in biota, therefore it does not build up in the food chain.
In the United States, the EPA drinking water standards report that the maximum contaminant level is 3 parts per billion, as established in 1993. This is due to numerous health effects in people. In the short term, atrazine causes congestion of heart, lungs, and kidneys, muscle spasms, weight loss, damage to our adrenal glands, and in the long term, atrazine can cause further weight loss, cardiovascular damage, retinal and muscle degeneration, and even cancer. The ecological effects are also particularly prominent, based on hundreds of atrazine toxicity studies compiled in an EPA ecological risk assessment published in 2016. Atrazine has negative repercussions to the reproductive system of mammals, birds, and amphibians. According to the EPA, various studies have shown that atrazine can chemically castrate and feminize male frogs, in addition to other effects such as mortality, growth or developmental alterations, reproductive trait alterations, and endocrine and immunological effects. These effects are particularly bad in aquatic environments, where atrazine use is the heaviest, due to the tendency of atrazine to leach into surface and groundwater.
We ran atrazine through the level 1 fugacity model. We used these physical and chemical properties for atrazine as inputs. When we ran the level 1 fugacity model, we used the default environmental properties and emissions embedded in the model. And these were the results we found. We noticed that atrazine was not inclined to go into the air or settlement, but was very prone to go into the water and soil. Overall, the atrazine was most inclined to go into the water. This was consistent with the results of our other research, which found that aquatic environments can be the most sensitive to atrazine contamination. So, what do these results of the fugacity model show, and what does that mean for remediation purposes? A primary concern is surface water mitigation. In an agricultural context, this translates to ensuring that atrazine runoff from farm fields is filtered before it reaches larger bodies of water. One way of filtering this water is with BMPs. Because atrazine is relatively prone to go into the soil acts as a decent removal agent in the BMP. The fugacity model results also indicate that timing sprayings based on predicted precipitation can help. Avoiding pesticide applications right before rain reduces atrazine runoff into the natural environment.